Right, good morning. So there's a bunch of things that people don't generally say. As you left me with the legacy systems thing, there is the question, why do systems become legacy? What are the properties of a legacy system? And this is actually something I run in workshops. I ask people what characterizes legacy? And I get people to list off properties of legacy systems. Because there are many things that qualify as legacy. We actually hide behind the word legacy to sometimes mean very, very different things. Two people using that term can mean quite different things. We can be talking about a system that is just using old technology that we don't like. We can talk about the word legacy to mean code that somebody else wrote that was not me. That's one of the most popular definitions. But one of the things that people sort of invariably end up with is at some point there's a kind of sense of size. And I'm going to pick on small today. Just of all the many things that we could talk about, I'm going to talk about size issue. Sometimes that relates to simplicity, not always. So I'm preempting the fact that sometimes people come up to me and say, yeah, but you didn't talk about simplicity, or you didn't talk about, that's fine. When you do a talk, you're supposed to stick to kind of one thing. But I will wander around quite a lot, physically and intellectually, hopefully. But people don't generally say, oh yeah, that legacy system, it's so small. They don't complain of like, oh yeah, the legacy system whose code base is about the right size. That's never a sense. There is always a sense of there's too much stuff. And that's an enduring idea. And so there's a question of sustainability. So I've shamelessly stolen the title. In fact, the inspiration, ultimately, for this talk comes from this book here, Small is Beautiful, published in the early 70s, 1973. Ernst Schumacher, an economist, who effectively created what we now think of as a more responsible form of economics, the idea that you don't operate in a vacuum, and that perhaps there's a question of sustainability, and so on. And it's a lovely old book, and I went back to it again recently. It's kind of interesting seeing the view from the 1970s now that we're in the 21st century, and how much he got wrong, but also how much he got right. And there's a subtitle here, A Study of Economics as If People Mattered. So I'm going to steal that. I'm going to go with Small is Beautiful, and, by the way, if you don't have kids yet, give them an internet unique name. They will thank you at some point. Okay? My parents managed to do this before the internet existed, which was a major act of prescience on their part, but you have no excuse. I've done this for my children. Okay? I did this when they were born. I Googled just to make sure that there were no hits on first name, last name. And, when my older son joined Twitter, Dad, what name shall I use? I said, just try your first name, last name, like I do it. He says, oh, it's available. I said, yeah. That moment was 13 years in the making. So you can offer this service to your children, okay? However, a talk on code as if people mattered. This is an interesting one. One of the most amazing things that we have discovered in the last decade or so, it turns out software developers are human beings. I know. I mean, how did that happen? But what that means is that human beings have a particular set of properties, comfort, how they interact with one another, that gets reflected in the code. We often try to think of the code as somehow separated from the people that work on it. And this also tells us about why things get out of control and get big. But there's also another aspect, a talk on code as if economics mattered. Because there is this idea that people are always chasing a deadline. There's always a reason why they're doing something the way that it is. Well, sometimes it's an excuse, not a reason. But it's worth actually kind of pulling this back and saying, hang on, does this actually make sense? Is this the right way to invest in development and do things? So that's kind of the bigger picture. Now, out of all this, I mentioned the word sustainable development, and kind of Schumacher's work ultimately led to this observation in the Brundtland report, headed by the former Norwegian Prime Minister, Gro Harlem Brundtland, in the late 80s. that was looking at sustainable agriculture, sustainable economies, and so on. And I'm doing something far less interesting here. I'm talking about software. But the definition of sustainable development is an interesting one because it's something we can appropriate. So when eventually the words agile and lean lose steam, then perhaps we can use sustainable as a way of kind of saying the same thing but giving it a new label. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So there, immediately we see that the challenge of development is to strike this balance. If you never have to worry about future generations, then that's fine. You can just put out anything and you're done. But normally we do have to worry about future generations. Even if it's not ourselves, there's normally somebody else who has to pick up the code. There's normally a release 2. What's that going to look like? And that becomes the question. It's not, but people are so focused on initial release and first release, and then the next release becomes another first release, without realizing that there's a whole procession of releases, and maybe that this is a system of releases, and maybe there's a better way to approach this. On the other hand, we end up with sometimes the overcompensating big architecture, the big enterprise projects, the global projects. I went through a phase of noticing and visiting companies, either workshops or even contract work, when I noticed that the word global kept appearing in their project names, or enterprise. And when a project acquires that name, you know it's doomed. Okay, it's just like, oh, this is going to be a no. So that's the point, is that that's the future that will never arrive. There's no present there. So there's this balance, and the balance is the bit that's hard. So let's explore this a little bit. Let's, first of all, start out with the idea that not everything is going to be small, but that everything has an appropriate scale. There is a right size for certain things. The question is, are we able to get to that size? This is ultimately an optimization problem. Here is the system you would like, and here is the system you've got. How different are those? Not just in terms of the physical sizing of things like the source code, which we're going to come to as being something that you need to put in your head, but actually in terms of the development effort. So we can get a real sense of this with a bit of Shakespeare. And seeing as we're in Denmark, I will choose Hamlet, Prince of Denmark. And so this is fairly classic. To be or not to be, that is the question. This is fairly classic. How would we approach this if we were writing this in marketing speak or business speak? Okay. Well, we have an answer to this question. Tom Burton, in his book, Long Words Bother Me, had a go. Continuing existence or cessation of existence, those are the scenarios. Is it more empowering mentally to work towards an accommodation of the downsizings and negative outcomes of adversarial circumstance? Or would it be a greater, et cetera, et cetera? And you know what? A lot of developers write like this as well. Oh, actually, they write like this. People have some really, really crazy ideas about how to lay out their code. You know, it's just, says, oh, look, I've got an IMAX screen, so I will push everything out over here, and I will use really long names to be really helpful. As we see, the bigger the word, it's not necessarily more impressive. You end up with homeopathic naming, where you add more and more to the identifier names, more and more, and you're diluting the meaning further and further until there is absolutely nothing left. So let's go back to this question of constraint and stick with Shakespeare for a moment. This is the monstrosity in love, lady, that the will is infinite, the execution confined, that the desire is boundless, and the act a slave to limit. So there is this idea that human imagination is pretty cool. We can imagine all kinds of things. The problem is that we are eventually confined to what we can deploy, what we can write, what, importantly, we can actually hold in our heads. That turns out to be the bandwidth limitation. What you can actually reasonably hold. So there is this concept that a good architecture, a good code base, a good piece of code is something that at some level you can hold in your head and reason about comfortably. The minute it overflows, the harder it becomes to reason about. And suddenly you slow down. You're more likely to introduce defects. You're more likely to introduce technical debt. You're more likely not to touch anything at all because you're just a little bit cautious. You're not entirely 100% sure you understand it. And that is how you create, that's one of the ways in which you create a large system. It's that kind of hesitancy, that fact that you cannot reason about it. This does not mean we do not build large systems. It just means that we have created a system that feels large, whereas you want to create a system that wherever you are, it feels local. You can grasp the concepts around you. So it turns out that this is your bandwidth. Now, obviously we can go to the extreme of saying, well, let's talk about ultimate smallness and ultimate constraint. My favorite example, which I've actually got an update for, is this piece of code. Start the day with a bit of assembler. I think some of you are still booting up, so something fairly low level like this should probably suit you. This is Z80 code. It runs on a ZX81. Runs, present tense, I guess ran. It's written in the early 80s, 1982, 83, by a guy called David Horn. This was referred to by a games developer, Thaddeus Frogley, as being the greatest program ever written, which is quite a claim, but it's actually it's fairly reasonable to consider that. This is a chess program. I mean, it's not exactly, deep blue, but this is a chess program. And it's done to fit in a 1K memory space. Okay, this is get an appreciation of 1 kilobyte. In fact, to be precise, this doesn't fit in 1K. It fits at 672 bytes because the runtime has to take some space. This is ZX81. So 672 bytes, that's 4.8 tweets. You can't even describe the rules of chess in 4.8 tweets. Yet this game, I mean, as I say, you might go to a few deep learning sessions. It's not exactly going to compete with those. But it can recognize a draw and a win. It can play the basic rules of chess, so I don't think it has en passant basic bits and pieces like that. And it can play against you. That's just impressive. Obviously, somebody forgot to tell David Horn this was not possible, so he went ahead and did it. Now, why is this even remotely relevant? Well, one, it's kind of fun. Two, I'm not going to claim that this code is brilliant. But the chances are is that the reasoning behind it, the very challenge that he has taken up, is the thing that we're interested in. Is when somebody says, oh, you can't do that, there's a very good chance that you can, and that the very constraint that you said you can't do that with will allow you to overcome this. So there's a very good case for this being exactly what it is. Now, I've used this example a number of times before of being a remarkable example of cool code. But actually recently, a couple of years back, indeed last year, Olivier Poudard managed to create boot chess, which fits in the boot sector. So it's 512 bytes. So that's even smaller, which is really impressive. So that's half a K. Yeah. Now, why is this relevant? Why is this relevant at all? Because obviously, I'm not going to say we should all write obscure code. We're already doing that anyway. It's called code for a reason. And obviously there's a particular aspect here. Such a thing is a work of art in one sense. It's a unique result of a unique temperament. But it is just a reminder that ultimately when you are creating things, as the Agile tester David Evans observed, your customers do not buy your software by the line. If they did, that would be great for some people. I mean, just type more. Just keep on typing. Because you look at some systems and you think, are they actually incorporating and encoding? Code is a word that we can play with. You are codifying business knowledge. You are codifying technical knowledge. You're bringing it all together. And yet sometimes you look at a piece of code and you're thinking, this is a really longhand way of doing this. You look at an interface and you think, this is a ridiculously overbearing and heavyweight interface. There's so much here, and yet for so little functionality. So there's these questions that come to mind. But the challenge should not be around this. There's something deeper that we want to kind of reason about. And we have these lovely examples about constraints. One of my sort of favorite classics in the sense of how people have created and reasoned about these things is this book by the late John Lyons, who was a professor at the University of New South Wales, if I remember correctly. In the 1970s, he wanted to run a university course on operating systems, and he wanted to run a real operating system. He wanted something authentic that was not designed for students, so he wanted an example from the real world. And he managed to get his hands on the recently released code, and there was no internet to speak of, but the code from the 6th edition of Unix, and then annotate it. He wrote it up and described it. As you can see, before it actually got published as a book, it was passed around by samizdat. People would basically photocopy the notes. Here's your whole operating system and annotations. Now, for those of you who are a little young, a photocopier is a kind of socialized scanning. Okay, you don't scan alone, you scan with other people. You kind of hang out in the university library hoping that somebody you know and want to talk to will come by, and it's a social experience. This was the premise here. But the key thing here is that the kernel was under 10,000 lines of code. 95% of which was written in C, was written portably. Only 5% of which was written in assembler. And this, importantly, at the time, this was absolutely, this is something you can't do. You cannot write a whole operating system that is retargetable in a language that is retargetable. This was a basic article of faith. It always has to be assembler, or most of it has to be assembler. But here we have the very kernel, not simply the shell, being expressed in a way that is portable. And we look back at the code, and you look through it, and you go, well, it's fairly antiquated C style. It's an era of very different conventions and what was defined to be good. And yet, at the same time, they did things like write code in separate files. That 10,000 lines is not all in one place. And yet, I see classes that have this kind of line count, if not larger. There are classes out there in systems that people have paid good money for. There are classes out there that have their own gravitational field. And we know about the planetesimal theory of planet formation. You have something there, and it has a particular size. Other things are drawn towards it because of the gravitational field, and it becomes larger and larger until you've got one hot Jupiter of a legacy system. Okay? You've ended up with this thing. It just grew. Nobody planned it that way. People don't, generally, I don't believe this happens, but if you have anything to contradict this, people don't sit down and say, right, okay, we're going to build a new system. How are we going to do it? I think we should have really large classes with lots of duplication. Absolutely. Should we make it testable? Absolutely not. Okay, I think we should, if you're struggling for a name for things, I think we should use names like manager and processor and controller and stuff like that, and scatter the responsibilities around the code, which will cause more duplication and confusion. And I think we should put a shed load of people on the project as well. And we're going to make this really obscure. Nobody will understand it. Okay, make it so. That's not how architectures are created, I hope. But there's a key point here, that there is a challenge here that was met, that in under 10,000 lines, they've been able to create an operating system. Whereas sometimes you look at something and what have you managed to do? We've managed to take a message and process it into a different format. I had that with one client. It's like, that's 20,000 lines. Good God, is this not a solved problem? So we have this observation that was made fairly early on in Unix's life. The late Dennis Ritchie and Ken Thompson, 71, 72 paper on Unix. There have always been fairly severe size constraints on the Unix operating system and its software. Given the partially antagonistic desires for reasonable efficiency and expressive power, the size constraint has encouraged not only economy, but a certain elegance of design. And this is the interesting thing, is that they're actually working with the constraint, not simply against it. And we often assume that a constraint is a negative thing to have. But I want to try and get back to the point of why I showed David Horn's program. It's not because I'm saying you should write obscure code and encode chess programs into small bits of your enterprise system. What I'm actually saying is that you can use seemingly arbitrary constraints as a benefit. The human imagination is indeed infinite, but the will is indeed confined. If you can find that constraint, you will probably find something of value to help drive the architecture. That thing of value may change, but once you have that, you have a driver. And we see this time and again. Donald Knuth observed, one rather curious thing I've noticed about aesthetic satisfaction is our pleasure is significantly enhanced when we accomplish something with limited tools. Okay, and as he says, makes a person feel like a real virtuoso to achieve something under such severe restrictions. But he's not the only person to make this observation. If we're going to talk about virtuosos, talk about Stravinsky. The more constraints one imposes, the more one frees oneself, and the arbitrariness of the constraint serves only to obtain precision of execution. You need to find the constraints in your system. They're not always obvious at the beginning. This becomes a hill walking problem. What you're trying to do is find the constraints that characterize your system and find the spaces that allow you your degrees of freedom. And once you've found that, then you've got something to work against. That will give you a more natural sizing. You can reveal the natural sizing of a system. So what is it that, in that case, stands against our assumptions? Well, it's kind of a nice observation from a programmer I know, Chris Allwood. Isn't a netbook screen a bit small? No, if the code doesn't fit on it, it's too complicated. And there's a big case for that. I want to go back to this observation I made earlier on, the way that sometimes people respond with how they structure their code. They structure it according to their available screen size. And these days for developers, that's quasi-IMAX. They're kind of sitting there in front of like triple-headed 4K resolution. And they're like, yeah, that's fine. I've got no problem with a name that is 120 characters long because I've got the screen for it. And it's like you're solving the wrong problem. The problem here is that there is a human being. It turns out we are humans. Much as our screen sizes have evolved, it turns out that the visual system has yet to catch up. And when you actually have to turn your head to read the end of an identifier, you know that's a bad sign. When a source line of code has its own microclimate that's different at the end of the line to the one at the beginning, that's not a good sign. So I did this with a client a couple of years ago. We were just going through the code. And actually, I'm going to say, most of their code was, it was within 80 columns, actually, except every now and then something would just go off. It was kind of funny looking at a sort of like a heartbeat or something. And you go, bip, and it would go off the screen. Bip, complex algorithm. Bip, what's that formula doing? So we went in search of the right-hand side. We got our blunderbuss guns and we got our appropriate hunting gear and we went out into the wild. We found a line that was 360 columns long. We kind of almost wanted to put an extra 5 characters in there so we have one column for every day of the year. And the point is that that's not human. That doesn't work with humans. And similarly, the way that sometimes people will hit the 160 column limit and say, 80 columns, that's just so 1970s. It's like, no, that's to do with human visual perception. I mean, if you actually care about how people read, it turns out, I'm going to give you bad news, 60 columns. So by saying 80 to 100, we're being quite generous. It turns out that we're much more comfortable around the 50 to 60. Look at how web pages are organized. Yeah? In other words, your source code actually defines an experience for a user. That user is a developer. And how does their visual system work? How are they able to chunk and reason about things? So there's a sort of a call here for some kind of balance and reasoning. But also this says something about our ability to break a problem down and to reason about it clearly. The sizing thing does matter. It's how easily you can grasp stuff. And I recall a visit to a company a couple of years back where they were complaining about their technical debt on day one. We were talking about technical debt. That's what I was there to talk about. And then there was this discussion in the evening. Went out for a meal, and I said, I'd really like to see some code. As we've talked about, we've drawn diagrams on whiteboards and talked about things, but I'd really like to see what the code is like. So I then paired the following morning with one of the developers. And, just sort of tweaked a couple of tests, looked at the code, and the code looked pretty good to me, I have to say. And then the moment that will always stay with me is he pulled up on screen a method. And it fitted on the screen. And he said, this, Kevlin, this is what I'm talking about. This is the problem. I'm kind of, yeah? He said, look at that, it's such a mess. It's so large. It's like, right, okay, thank you. You have calibrated your system for me. If this is the worst you can show me, you do not have a technical debt problem, okay? there are people that would kill for methods that fitted on a screen. This was the worst he had to show, and yet you could reason through it. Yeah, it was a bit tricky in places, but that was actually a reflection of the nature of the problem, not a reflection of source code chaos. It was not a reflection of muddled thinking that had started down that road of like, I'm not sure what's going on here, let me add something rather than modify what's in place. And so there's that idea that these seemingly arbitrary constraints can help us to reason about things. Obviously, you have to respond in a reasonably rational way. Don't do what I didn't meet this guy, but it was at a place that I used to work, and it's far enough back that when people talked about the size of procedures or methods in code, they would talk about printed pages. And the idea is that the routine should not go over a printed page. So this guy responded in the way that many developers would, with ingenuity, and he worked around what he saw as an arbitrary constraint. So he'd write the code as he wanted, print it all out, and then just mark off the boundaries, and then break all of the procedures at those levels. Yeah, so you'd have an arbitrary point and call the thing 2 at this point. That did not have the desired effect. That's not the kind of constraint we're talking about. But we can take this further. I've talked about code locally. What about the idea of creating a whole product based on this kind of thinking? What about the idea of actually introducing an idea to the world? This is interesting that John O'Dell, former editor of Byte magazine, a couple of years back, he was reflecting on Ward Cunningham's wiki, and he said, here's the original email. 19 years ago, I received this email from Ward Cunningham. John, so what do you think of Wiki? I put it up a year and a half ago when HTML authoring tools were in short supply. I think it has held up pretty well, though I suppose its days are numbered. It turns out the number's quite large. Still, there is something about it we call wiki nature that is in short supply on the net and in computers in general. And that is still true 20 years on. There's something really profound. What Ward did was, this is the top and tail of one of the early versions of the wiki. And I used to hang out on the original c2.com wiki. It was quite a little community there, but it actually turned out to be quite useful. And there was an ease of use about it that came from the introduction of arbitrary constraints. You couldn't just put HTML into it. It was not an HTML authoring tool. And it had a very simple model of links, simplistic even. In fact, it's so naive that it's amazing it got popular at all, but that's the whole idea. There's an idea here that I want to pick up at the end about the simplicity of the approach that led to something that was easy to discard. We don't talk enough about discardable code. We sometimes talk about throwaway code, and that never gets thrown away. Have you noticed that? We use metaphors so badly. It's just like, yeah, I've just written this throwaway code. Now, what normally happens is that throwaway code becomes your system. Or in a good case, you might have just messed about with something, throwaway code. Your colleague comes to you 6 months later and says, oh, you know that throwaway code you wrote 6 months ago to do blah, blah, blah? And you say, yes. Could I have a look at it? He says, yeah, absolutely no problem. Now, I want you to pause for a moment and think about the word throw away. I threw it away, but here it is 6 months later. It did not fall into a time vortex to reappear at this point in time. What happens is we didn't throw it away. There's a very simple concept in the real world of what throw away means. It means when I throw it away, I can't get it back. We don't throw these things away. We generally hold on to them. But there is an idea here of a property that we don't value enough, discardability, the ability to say, here's a piece of code, and that kind of worked out fine for us, but now I've got a better idea, and I'm happy and free to throw that away. Just purely from a human point of view, the larger that thing is, the less likely you are to throw it away. Okay? The bigger something is, this leads to the sunk cost fallacy, the bigger something is, the more effort it acquires around it, the less likely we are to throw it away, the less likely we are to experiment with it, the less free we feel. Because in truth, we don't really throw things away. We just have different versions of things. That's one of the fascinations of software development, and probably one of the reasons quite a lot of people in software development enjoy science fiction in one way or another. It's the fact that you get to play with alternative realities on a daily basis. You get to play with constructed worlds. You get to time travel. I mean, you know, that's quite a big deal. Yeah? There's this whole idea that in other disciplines, they don't get to time travel, whereas we can go, oh, I didn't mean to do that. Let's go back in time, step into the TARDIS. Unfortunately, we don't have that kind of ceremony that makes it sound exciting, but it would be kind of cool if every time you did an undo, you kind of got the kind of warping sound of the TARDIS. Yeah? Just to remind you that what you're doing is actually quite interesting. You are traveling back in time. You can go into your repo and go back in time and navigate into an alternative reality. We don't play enough with that idea. It's a fundamental advantage. It allows us to create small things and throw them away. So this is the top and tail of the original Perl file for the wiki. So the wiki was made in Perl. I mean, good grief, it's my least favorite language. I'm not even sure it is a programming language. So a friend of mine once described it as executable line noise, and I think he's still right. But it's 150 lines of code. That's the top and the tail of it. And yet, I want you to imagine if you'd given that to a team in an enterprise-y organization. What we need is an interactive, editable web thing. Okay, we'll get back to you in 18 months. And then they overrun by 6 months. This is just so small, it's so ridiculous that it's an idea that surely could never work, and yet it does. And it has the opportunity to grow because of this. So Hemingway kind of had it right. Eschew the monumental, shun the epic. All the guys who can paint great big pictures can paint great small ones. So this is this problem that what we've ended up with is a sizing thing. Today we suffer from an almost universal idolatry of giantism. It is therefore necessary to insist on the virtues of smallness where this applies. But the problem is it probably applies in more cases than we respect it. And that sometimes when you get a conversation with people, what you'll end up with is, you know, I do a session like this at a conference, or I say something at a workshop at a company, and somebody go, oh yeah, I hear what you're saying, but our system is special. It's 10 million lines, it's 500,000 lines, it's whatever. And we're special, so therefore we can't do that. Trust me, everybody is a special snowflake. That's the whole point of software. Software development exists to create differentiation. It's not a manufacturing process. So everybody's ultimately going to be different. And everybody's working against interesting constraints. But the problem is people will weigh in and say our system is special without ever really asking, why is it so specially large? Why is it that you have had to organize armies to do the work? Which kind of leads to the question of why do these systems get large? Now, we looked at a couple of reasons, but let's take a different tack. I'm going to borrow from a friend of mine, Alan Kelly, who's been making a very strong case for this understanding of the economics of software and the economics of team sizing and team effort. And he says software development does not have economies of scale. If anything, development has diseconomies of scale. And this is quite difficult to reason about because from a very early age, we are ingrained with the idea of economies of scale. It's kind of part of the language. And the example he uses is this idea of, you know, if you get he uses milk cartons. I'm more likely to use wine glasses. Okay? But there is this idea that if you ever buy a bottle of wine in a restaurant, if you were to buy the equivalent number of glasses, the cost of the glasses would be far more than the bottle of wine. There's a natural economy of scale. I'll sell you 10 for the price of 8 for something. My youngest son had to do this exercise at school where they went away and did this little project and invested money and then tried to sell things to other kids and parents and all the rest of it. This is what happens when you do Brexit, you've suddenly got to figure out where the hell's the money going to come from. So now we're, child labor. But if you want any pencils, my youngest son can do a really good deal on them because that was one of the things that he and his best friend came up with was, what we'll do is we'll do a special offer. We'll give you 5 pencils for the price of 3. It's like, wow, that's pretty good. He's understood economies of scale. That was before he turned 10. It's ingrained into us very, very deeply. So there's this idea that when somebody says, we need this software system, it's just like, right, we need bigger architecture. We need bigger teams. We need more people. We don't even know we're doing it because it's so hardwired into the spine of our thinking. It's not even happening up here. Okay, it's down in the reptile brain. So there's this challenge that we need to kind of pause and think, well, maybe this is not the way we do it. Maybe what we're doing is we are thinking with or through ideas, and what we call thinking is generally the application of pre-existing ideas to a given situation or set of facts. We look at a situation through a lens of experience and habit, and perhaps we need to challenge that. And never underestimate how much force the situation of your existing ideas and also the organization around you exerts. Now, it has become traditional to refer to this paper, so therefore I do it slightly differently. This is actually Melvin Conway's original paper, How Do Committees Invent, in 1968. So it's not some kind of retro look that I'm after here. This is actually genuine retro, before the moon landings, just to put this in perspective. And Melvin Conway made this observation that has been observed casually, but also since verified a number of times. The basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structure of these organizations. In other words, the way that your system will come out is to do with the way that you arrange your people and how the people communicate with one another. And this is an important idea because it is how people actually communicate that he's saying here. The problem is that we have an idealized view of organizations. We think that the way that people are organized follows something like an organogram, a hierarchical decomposition. You have departments, you have the root of the company, and you have department heads, and then you have people who actually do the work, and it's all beautiful. And in some companies, this appears on PowerPoint files. In other companies, it appears plastered on the walls. If you wanted to know, I just referred to Brexit. The greatest achievement of the Brexit department, yes, we have a department apparently, over the whole summer was to produce an organogram of who they'd hired. That was it. They hadn't done anything else. But it was a very pretty diagram. What they were doing was offering the illusion that there was some reality here, that this was the reality. Organizations do this. There's a problem, though. That's the organization as you would like to perceive it, according to pay grade, line management, and all the rest of it. But let's take a slightly different observation. It's taken from a book, Design After Modernism, which is a slightly unusual cover, to say the least, by John Thacker. It's a collection of essays. In it is a rather interesting essay by Christopher Alexander, A City is Not a Tree. And this gives us a different insight into sometimes how we can think about architecture. When we talk about architecture, we normally think about a single space within an urban space. We use the metaphor to refer to buildings, and we talk about buildings an awful lot. And indeed, this is the same Christopher Alexander that was responsible for this idea, timeless way of building, patterns. He's the guy responsible for that. So it's the same guy, and he's interested in systems of thinking, overlapping thinking, how one design idea can lead to another or support or negate another idea. And that we're not thinking just in terms of modular parts, we're thinking about how a system actually overlaps. And as he observes, he says, the tree of my title, as in a city is not a tree, is not a green tree with leaves. It is the name of an abstract structure, at which point the whole room suddenly becomes comfortable. Okay, yeah, we can do that. Yeah, we're good, because as you and I know, trees, their roots are at the top, their leaves are at the bottom. That's the true way. And if trees have color, then it's red and black. Okay? This whole green trees with roots at the bottom and leaves at the top, that's some kind of real-world aberration that we just target with CGI. You know? But the real trees are these. They are abstract structures. And he wants to contrast it with the semi-lattice. They're ways of thinking about how a large collection of many small systems go to make up a large and complex system. And as he then observes, well, look, this is actually what goes on. In a real organization, people they don't sit within a hierarchy. That's not how they live and breathe the system. It's not how they communicate with people. It's also not how the code grows, because the paths of communication will emerge from that. Now, you have a choice here. You can either acknowledge that this is what happens, and therefore, you can organize your architectural effort around that, or you can be surprised by it every single time. It turns out that where people sit, who people know, who people trust, who has certain expertise in some things versus others, who is easy to communicate with. All of these kinds of things will ultimately start shaping the system. And we haven't even started talking about the requirements and how you choose to deliver. So there's this idea of complexity, which is why people shy away from it. Semi-lattice is potentially a much more complex and subtle structure than a tree. The reality of today's structure is thick with overlap. The systems of friends and acquaintances form a semi-lattice, not a tree, which means that although we may envisage a system and decompose it rather elegantly into smaller and smaller parts, and if you look at every single paradigm of development, they're always about decomposition. And somewhere in there is the concept of a tree, and we find it valuable. It informs the syntax of our languages. It informs the way that we indent code. It's certainly valuable on a local basis. But the problem is that reality is a lot messier. So you've got a choice. You can either say, I deny reality and we're going to force it this way. You can say, no, reality is like this. It is a bit messy. How do we organize the messiness and yet still get localized order? That's non-trivial. That is exactly, as Christopher Alexander says, subtle. Because if you don't respect it, you will end up with some surprises. You will end up with the surprises that occur when you don't respect this dynamism, if you like. We've seen that this fact has important implications for the management of system design. A design effort should be organized according to the need for communication. If we don't, then our code will reflect this communication. It will reflect the mismatched, messy communication. What is communication? It is the transmission of knowledge. No, that's good communication. There's an awful lot of communication in organizations that is not about the transmission of knowledge. It's to compensate for the organization's inefficiencies and attempt to be hierarchical, when actually it isn't quite hierarchical. So there's this idea that sounds like just pure business speak, but what I'm saying is it trickles down into the code. As was observed in this paper in 2007, the MIT Sloan Management Review has a website, and you can kind of go to it and read one article. If you're going to read one article for free, this is the article you want to read. It's still remarkably relevant. Avoiding the alignment trap in IT. They make this observation, having looked at a number of large companies. IT's effort to satisfy its various and sometimes conflicting business constituencies created a set of Byzantine overlapping systems that might satisfy individual units for a while, but did not advance the company's business as a whole. What they're looking at is the fact that organizations often ended up with alignment that was local, but also against other groups. And they say, we have a strategy, we are business aligned. The thing you need to remember is that in an organization is made up of people. And we have a nasty habit of oversimplifying. It's part of the abstraction nature of humans. We sometimes talk about the customer, as if the customer was a single entity. In most cases, the customer is an organization filled with individuals who don't all agree with each other. And that gets quite interesting if you say, we are going to follow the organization's lead. We have a vision for the organization. It turns out everybody's pulling in different directions. Which leads to this, which also starts telling us how systems can get messy, or tells us again how systems can get messy. And obviously, at this time of day, I'm not going to present anything more complex than a quadrant diagram, because quadrant diagrams are easy. They divide the universe into 4, and normally there's one very, very good quadrant, or perhaps there's one very, very bad quadrant. In this diagram, we have both. Okay, and there is a simple idea. We're going to, based on a survey of over 500 companies that had some kind of software development and IT capacity within them, as opposed to, say, software houses or consultancies, 2 axes. Alignment with the organization. Is your IT aligned with the organization strongly or weakly? And effectiveness. How good are your teams? How good are their practices? This is not a judgment on how good are the individuals, because as we know, you can get a lot of people together collectively and they can actually act dumber than any of the individuals. In Britain, we call this a referendum, for example. And also, there's the England football team. Individually, they're actually quite good players. Collectively, they can be beaten by Iceland. Okay, so the point there is that it is quite possible to have a group of people be far less effective than the individual capacities suggest. And this is about coordination, about the necessary communication that you get. And so the observation here is, one element of the observation is unsurprising. Most teams, 3/4 of them, are in the bottom left-hand corner. They're not particularly aligned, they're not particularly effective, But it turns out, from a financial point of view, that's not particularly bad. They're not really gaining money, they're not really losing money. In fact, they're probably in equilibrium with an equally inefficient set of other departments in the organization. Everybody's reached a kind of comfortable equilibrium. They all suck equally, but they're happy with it. That's good. This is where most companies are. What people want is the top right-hand corner, which is 1/10 of the size. Okay? In other words, these guys they're getting cheaper and they're generating more revenue. This is fantastic. Everybody wants to go up there. Now, there's another reason I chose a chess program near the beginning. This is a bit like chess, except you don't get to be a bishop. You get to be a rook. You can only move horizontally or vertically. If you're in the bottom left-hand quadrant, would you like to become more aligned with the organization, or would you like to become more effective at software development? The standard answer from many consultants is become more aligned because everything else will follow. I'm sorry. That's the alignment trap. You've just walked into it. It turns out that you have taken a group of people who are not necessarily coordinated as a whole, who don't necessarily have the best development practices, and you've just thrown them to the lions, and they've got eaten. That's what those numbers are. What happens is that they're never able to recover. They're always worrying about delivering in the present, and they're never able to kind of say, you know what? We could step outside this vicious cycle that we've got ourselves in, and there's a different way to approach the architecture. There's a way of approaching technical debt. We can improve the testing, we can improve the deployment, we can improve our skills, we can review, but we don't have enough time, so none of that happens. And it gets worse. You've become an amplifier for the bad practices. Sometimes people describe certain development processes. This is a popular one in the Scrum world, a process that shows you the dysfunction of your organization. That's one of the most frustrating phrases you can ever throw at a group. You know, they're struggling. We're trying to do stuff. Well, Scrum is revealing your inefficiencies to you. Yes, we know, but that doesn't tell us how to solve them. There's a frustration there that all we've done is said, yeah, you see that problem you thought you had? You have it. It's like, thank you. Whereas it turns out that if you decide to become better at what you do, it turns out that has its own benefits. And that doesn't necessarily mean that you're not delivering useful value to the organization. But you're more likely to be able to do that. And this goes back to the release 1 versus release 2 thinking, that not everything is release 1. The idea here is imagine, simple thought experiment, a system that has been developed by top left-hand and bottom right-hand teams. They've developed the same functionality. Whose do you think is going to be most likely to meet the requirements? Quite possibly these guys, because they've been aligned to the business. In fact, the business won't shut up. So they really know what is required. These guys might miss. They might miss some key requirements and assumptions. Okay? Who's got better code? That's these guys. Better deployment practices, better quality, better management and explicitness of all the things that are invisible in software development. These guys. And so, what's their code look like? Those guys over there are going to have a nightmare. If you want to then join the team, join this team, because when they say, you know what, we realize we missed some key requirements. Oh, that's easy. We've got the tests, we've got the code, it's all good. It's small, it fits in our head, we know how to change it, and you're done. Whereas these guys over here, they've got this Jenga tower. Yes, that is now a style of architecture. They've got this Jenga tower of architecture of like, don't go near it, but I need to fix a bug. Don't go near it, because if you fix the bug, the whole thing falls down. And certainly don't add any functionality to it. So there is this idea that the thing on that side over there is going to start getting larger and messier. It's just going to become a challenge. So the sizing aspect is what we've walked into. How else do you create a big system? We've talked about the idea of communication. We've talked about the idea that sometimes the code artifacts themselves start attracting stuff, but there's other ways we can do this. And this again goes back to questions of economies of scale. How do we reason about how we organize an effort? So let's just imagine, a very idealized example. This is how much time it's going to take one person to complete all the work. All the work. I'm going to include in this all aspects of a system, including reasoning about the requirements and all this kind of stuff, deployment, testing, the works. So we then apply classic division of labor. We divide by n. We've got n people on the project. And most people stop there. And the problem is that's not how it works. Not everything can be parallelized. Not everything, when you put more people on, it turns out they start stepping on each other's toes. Sometimes that's physical. Sometimes it's in the code. Sometimes it's how they work. You end up with this, which starts looking a bit scarier. When you start showing this to managers, it's like, oh, equations. It turns out, though, that's quite important. How much can you actually do in parallel? How many wait states are there? How much flow can you get out of the system? It turns out the Kanban people were right. You can do this from first principles. In fact, we already knew this. This is Amdahl's law. But I've gone and robustly applied it to people. It turns out that this is going to reflect on your architecture, but it's also going to start creating, it's going to start exerting a force back on your architecture. People will continue working even when they're waiting. They will start creating things. They will start creating defenses. In fact, it gets more interesting because there's more equation. They will start creating defenses against the question of communication because it turns out you have to talk to other people. I know. Who thought that was going to be a consequence? You've got to talk to other people. That's the number of connections you have. The more people you have, the more connections you have, and it shoots up, and there is a cost to communication. This is reflected in the code. Code ultimately becomes a form of communication. Code is a form of communication. You're transmitting knowledge. You're not merely telling a machine how to execute. You are organizing your thoughts. It's a collective effort to create a belief that executes. This is how we believe this technology will run and answer a business need. And the problem is it interferes with the nature of humanity if we are not careful. You end up with a nice curve like that, which kind of fits our intuition because it turns out that, if you have 0 people on a project, it will take infinitely long to develop. But hey, no bugs. But then as you start adding people, you find some kind of optimal size that actually you have got the right number of people to do this work, to do this undertaking. The problem is that it's not a this is obviously very idealized. People are not all the same. They don't all have the same abilities. And you can't see the curve, and it's not perfectly smooth. So you don't exactly know when you're here. And you may find yourself wandering up the wrong side. And this is how you create large systems. This is a really easy way. Lots of consultancies. Hang on, quick check over here at the sponsor list to see whether or not I'm insulting anybody. Actually, I might be, but I'll keep them quiet. A lot of consultancies operate on the right-hand side explicitly. In other words, we took your small problem, we've made it a large problem by adding enough people to make it a large problem. I bet I could make this room develop a Hello World application, the like of which the world has never seen before and would never want to see, simply by scaling the problem up. It's not a problem that wants to be scaled up. It's a small problem, and it needs to be met with a small team and a small technology. And the point there is we're very bad at doing this sizing. But once you start running up the right-hand side, then it becomes a self-fulfilling prophecy. Because eventually that system becomes the 60 or 70 person system. And you can say, well, hang on, if we were to rewrite it, how many people will we need? Well, we've currently got 60 or 70 people on this, so maybe we need 60 or 70 people. It's like, no, you need probably about 10. And we have actually seen these experiments run out in practice, accidentally sometimes, and actually seen them in the real world where 2 companies, or in one case, one company that I turned a job down for because I thought there is no way these guys are ever going to deliver anything sane or sensible, and I don't want to work for them. And then 9 months later, a friend of mine went for a job interview there, and so I had a chat with him, filled him in. I said, this is what they were doing, this is probably what they're doing now. So he knew he was walking into the lion's den, but for him it was practical. They were 10 or 15 minutes walk from his house. So it's actually, for his point of view, that's what he values, being close to home. Okay. So sometime later, he told me, yeah, we've got about 90 to 100 people developing this system. And we've just discovered that in the north of England, the same company, because remember, companies are not single unified entities, they have no idea what they're doing. The left and the right hand are very, very different. In the north of England, another development team had developed functionality, or a system with exactly the same functionality with 10 people in about 6 months. These guys had spent 3 years and 100 people. And there are loads of examples like that over the industry. They had created, by staffing it up to 100 people, they had fulfilled their own prophecy. It did become a system that needed 100 people to create. And once you are there, it's very difficult to come back down again. I also had the benefit, the joy of working for somebody in my, many years ago who actually knew this. He took a team that was late and halved the team size, and they went back on schedule. You know, you hear about these things, but I can say firsthand, it's real, I've seen it happen. He was hated by the rest of the management. Yeah? Because everybody else was going by the easy bit of the equation, T1 divided by n. But he actually said, no, wait a minute, I think we've created the size. The size is not a reflection. So there's a point here, the size is not a reflection of the functionality. Once you reach a particular size, anything beyond that is no longer a reflection of the functionality. And there's this idea that a larger system has more functionality. Actually, we've seen time and again this is not the case. What we've seen is that above a particular size, the rest of that size is there to compensate for something else. It's there to solve a problem of organization. So I came across this one last year. The Facebook iOS app has over 18,000 Objective-C classes. 18,000 classes, not 18,000 lines, 18,000 classes. And in a single week, 429 people contributing to it. Now, I'm going to take a wild guess. I don't run an iOS phone. I've got an Android phone. I'm going to take a wild guess that it's not radically different on Android. But if any iOS users want to tell me what the extra few thousand classes are doing that I'm somehow missing out on, please let me know. Because that is just insane. Earlier on, we looked at an operating system, I don't know, some trivial thing called Unix, whose original kernel was less than 10,000 lines. In fact, the 5th edition, it was 5,000 lines. And I'm not saying everything can be made trivial, but there is a kind of a sense of perspective that you need to get. This does not only have its own gravitational field, this is actually at the heart of a galaxy. This is one of those black holes, okay? There are hundreds of millions of stars orbiting it as a result. And that's you just thinking about what on earth are they doing? I mean, it's one of those things, I don't want to make it sound too trivial in the sense that, what are you doing? Well, I'm looking at friends' pictures and, you know, pictures of cats and goats and things like that. And I'm posting some things and I'm liking a few things. I mean, how much, that? There's something really special going on there, and I don't think that's 17,000 classes worth of NSA stuff, okay? So we have this kind of interesting challenge that we are looking at a number of interesting practices. There's organizational things, but there's also how we approach things, our habits, our non-thinking, where we started this. Cargo cult programming, style of computer programming characterized by the ritual inclusion of code or program structures that serve no real purpose. Cargo cult programming can also refer to the results of applying a design pattern or coding style blindly without understanding the reasons behind that design principle. And suddenly, without realizing it, you've turned a one-line problem. Oh, that's too easy. You've turned FizzBuzz into FizzBuzz Enterprise Edition. It's one of my favorite sites. I did actually have to point out, so I will point out to you, this is a joke. I mean, it's got real code, it does compile, but it's not intended to be real. You know, and there's tongue-in-cheek, enterprise software marks a special high-grade class of software that makes careful use of relevant software architecture design principles. This project is an example of how a popular FizzBuzz game might be built were it subject to the high-quality standards of enterprise software. The whole thing is in quotes. Okay, you have to read it like that, because you end up just looking at one of the areas. This is just some of the interfaces in one corner of the system, yeah? We're in the factories interfaces section, and we've got such fundamentally important plugins as integer string returner factory and string returner factory. Oh yeah, there are factories as well. Anderson's law observes there are two aspects to this law. I have yet to see any problem, however complicated, which, when you looked at in the right way, did not become still more complicated. One aspect of this is that it's turtles all the way down. Some problems genuinely are deep. But the other is a self-fulfillment. We can make a simple thing hard. We have decades of experience doing this. In fact, we're not alone in this one. The American architect, building architect, Philip Johnson, observes architecture is the art of how to waste space. And you know, sometimes you look at something and go, yeah, actually that might be a good description of what's going on. There's a very simple idea here. Paul McMahon kind of observed. All code is technical debt. Some code just has a higher interest rate. That's what you're interested in. When people sort of say, oh, how much technical debt have you got? That turns out not to be the real issue. It's part of the issue. If you are dealing with a piece of code that has high technical debt, or rather, sorry, if you have a piece of code that you never touch, then its technical debt is low, or its interest rate is low, because you never interact with it. It does not cause you pain on a daily basis. If you constantly interact with something that has high technical debt, that has a higher interest rate. Because it's causing you pain on a daily basis, you're having to pay out extra every single day. But that code that's not doing anything, is it really not doing anything? Does that not mean that, is it technical debt that we have a problem with there, or is it something else? So I want to close with a sort of consideration of an example that one of the other problems that we have when we talk about the dead parts, the dark matter of our system. Okay, in any large system the galaxies are not simply shaped by the black hole in the heart. They are shaped by dark matter, stuff you cannot see. Code you do not understand, but also code that is not executed. Knight Capital Group, 2012, experienced a slight blip, I think would be an understatement to say, on the 1st of August, going from 31st of July to 1st of August, on the New York Stock Exchange. And there's a very good blog, Doug Seven wrote this blog from a DevOps perspective. Knight Capital Group realized a $460 million loss in 45 minutes. $10 million a minute. Excellent. Yeah, that's the great thing about computers. You know, they can amplify basic human error. It's very difficult for an individual human to actually lose that, okay? Donald Trump spent years losing twice as much as this, okay? But what you can do is you can actually optimize it. Computers can let you do the wrong thing faster at ridiculous speed. They realized something was going wrong, like, quick, pull the plug. 45 minutes later, they did. They actually lost more money. This is how much was left. This is how much the loss was after everything had been rolled back that could reasonably be rolled back. And what happened? The update to SMARS, a system, I think they had 8 servers, was intended to replace old unused code referred to as PowerPeg. Functionality Knight hadn't used in 8 years. So there's dead code. This is the problem, is that they had 8 machines, 7 updates were correct, 1 of them was not. So it ran old code. And what they did is they recycled, effectively, a piece of protocol. We're going to reuse that because nobody's using it. Yeah, because it's safe, it's easier than adding something new. We'll just recycle that. Problem is it has meaning to the old system, and not the right meaning. Yeah, we just recycle old ideas, but the problem is we left the old code in place. Now, what I think is interesting, and where I disagree with this assessment, and what tells us a little more about the graspability, the in-your-head-ability of this. Why code that had been dead for 8 years was still present in the code base is still a mystery, but that's not the point. Actually, it is. How did you end up with this dead code? This is not, it's zombie code, basically. If you think you have dead code, it's probably zombie code. What would cause this code to resurrect and come back to life? And a particular set of circumstances caused this. So it is actually the point, because the idea is that this would not have happened. It was not just a bad update. It was a bad update and the presence of the code. The point here is this was a perfect storm. It was not this or that. It was this and that. What happens is in systems which we have effectively lost intellectual control over is you increase the probability of cases like this. That's what's going on. And then boom, you get a big surprise. So ultimately, just to demonstrate there is no new idea under the sun, I'm going to go back to the 1990s. I mentioned patents before. Richard Gabriel, key member of the patents community, wrote this book. No longer available. The PDF is available. Very interesting series of essays, one of which he talks about his approach from 26 years ago. Worse is better. I proposed a theory called worse is better, why software would be more likely to succeed if it was developed with minimal invention. Problem is with the phrasing worse is better, you immediately think, well, worse. I mean, it's the wrong name for it. But when somebody says it is far better to have an under-featured product that is rock solid, fast, and small than one that covers what an expert would consider the complete requirements, he's talking about something fundamentally different. He's talking about a philosophy that fits the Wiki way, the Unix way, and indeed, the way that a lot of people now think of as lean startup. He focuses on implementation characteristics because that's where developers live. Developers will ultimately produce a system. Of course, the customer experience is important, but ultimately somebody needs to develop it, and you need to make that amenable and possible. It should be fast. It should be small, because then you can throw it away. You can understand it and think of better ways of doing it. It should interoperate with programs and tools the expected users are already using. Minimal invention, he's saying, something very modest. The Wiki way, for example, did not define a fundamentally new browser concept or paradigm, but it helped us understand what we might want from one. It should be bug-free. This is what worse means. Worse means fewer bugs. Slightly counterintuitive. But there's that idea of, if you want to make it smaller, reduce feature set, that's easier to manage. And don't get carried away with abstractions. It's a very simple idea. So I want to close with this kind of observation that we talk about incremental development a lot. I'm very interested in an idea called decremental development. Okay? We should learn more about how to throw things out, more about that was our first attempt, now how do I size it down to its natural sizing? And I'm sure over time it will get bigger. The problem is that what we do is we start in the wrong place. And I'll give Schumacher the last word. Thank you very much.